Today we're going to be talking about solving logarithms. So these are going to be equations that involve exponents that we're going to try to get rid of their bases by using a logarithm, or logarithms that we're going to try to get rid of the logarithm using the base of an exponent. So let's go ahead and get started. Right here we've got several examples that are going to help us understand how to use the log and exponent bases as inverses. Okay, so first thing you need to remember is with log is asking the question, what power? What power of my base would equal this? So in what I've written here, what power of 2 would equal 2 to the power of 3? Well, that should hopefully be obvious. The answer was in there. 2 to the power of 3 would equal 2 to the power of 3. Therefore, the answer is just 3. Now, notice what happened in that evaluation. The log with the base 2 and that base of the exponent of 2 eliminated and just left us with 3. Here, this log is asking 5 to the power of what is equal to 5 to the power of 7? So once again, 5 to the power of what would equal 5 to the power of 7? Just a 7. And once again, the log base 5 and the 5 to the power are taken out, and the only thing that's coming over is that 7. Over here we got something trickier. Now, even though it's an 81, let's go ahead and switch that up. I can get an 81 by multiplying by 3's. So if I did a 3 times 3, we get a 9, times 3, a 27, times 3 is an 81. So we can switch up that entire equation right here to be saying that the log of a 3, log base 3 of 3 to the power of 4 is going to equal what? Well, 3 to the power of what is equal to 3 to the power of 4? 4. The log base 3 and the exponent base of 3 eliminate, and we're left with 4. Now here we've got that x. Well, what's going to happen here? 9 to the power of what would equal 9 to the power of x? X is that answer. 9 to the power of x would equal 9 to the power of x. Once again, notice the log and the exponent base will eliminate, so long as the base of the log is matching exactly the base of the exponent. So what we see here is how log could be used to pull exponents out of a variable exponent, out of the exponent, and just leave it alone. So this is how log can be used as an inverse to eliminate certain values. It also works the other way. Okay, so let's look at these. Now we're going to evaluate several of these pretty easily. We'll use a couple steps. So first I'm starting in just that exponent up there. So 5 to the power of what would equal 25? Well, that would be, the answer would be 2. So log base 5 of 25 is equal to a 2. And then 5 squared would just equal 25. Now, look at what happened. Okay, the base of 5 and the log base 5 eliminated each other because they are opposites and left us with a 25. Left us with what was inside that log. Right here, we got 2 to the power of what would equal a 4? So just evaluating that exponent first, log base 2 of 4 should equal 2. And 2 to the power of 2 is 4. And once again, notice the base of 2 and the log of base 2 eliminated, and we just got the 4. 3 to the power of what is equal to 243? Well, that would be 5. So then we'd get 3 to the power of 5, which is then equal to 243. The base, the log, eliminated, and we just got that exponent. Now here I can't eliminate, I don't know what 7 to the power of what would equal x. So I don't know that, but I do see a pattern here. If my base of this exponent matches the base of the log, so we're raising 7 to the log of 7, those will eliminate, leaving me just with x. Now we are going to use this property that I've just shown of how logs can be used to eliminate the bases of exponents and how the base of an exponent could be used to eliminate a log in order to solve more complicated equations. So let's go ahead and actually, we'll start over here. This one involves a base of e, and I want to talk a bit about that, but let's start with something more simple, with just a normal number. Now, first thing I'm going to do as I'm looking at this, I want to identify where my variable is. So it's over here on the left-hand side, so I know I'm eliminating the numbers that are over on the left. More specifically, it is inside, it's inside that exponential statement. M is inside the exponent. Before I can get to M, let's get rid of the other numbers that are there. So we see a plus 8, that's minus 8. And then we'll get negative 97. Okay, now we've got this multiplying by a negative 3, so we will divide both sides by a negative 3. So now I have 9 to the power of m is equal to, and negative divided by negative will be positive, so 97 thirds. Now what we're going to want to do is eliminate the base of that exponent. Because certainly I am not going to be able to figure out 9 to the power of what is going to equal a 97 thirds just in my head. But that's exactly what a log can ask. So we're going to do log of base 9, because the base of the exponent was a 9. And if I do it to one side, I need to do it to the other. So what's going to happen? The log base 9 and the base of that exponent are opposites and will eliminate. And then we're left with the log base 9 of 97 thirds. So let's go ahead and let's type that in to our calculator. Log base 9 of 97, let's use parentheses, 97 thirds. So 1.582. And actually I should change this away from equals because we rounded. And it is approximately 1.582. Okay, and there we were using a logarithm in order to get x out of that exponent. So let's do it again. Over here we've got 9 times e to the power of x minus a 3. Once again, get your exponential statement alone first. So we'll go ahead, add this 3 to both sides, which will leave us with 9 times e to the power of x is equal to 13. We can divide both sides by the 9 to get e to the power of x is equal to a 13/9. Now, just like we did before, I now want to take the log of both sides. So what I would be doing is doing the log, and I want to match the base, so log of e. Now, something you should remember. Log of e actually has its very own name and its very own symbol. So I'm going to rewrite it using that. So rather than putting log of e, we are going to replace it with the natural log, which is just written as ln. Okay, it means the same thing. The natural log is just log with a base e. Because this is log with a base e, and that's an exponent with a base e, those will eliminate, leaving us with x is equal to the ln of 13/9. And now let's go ahead and we'll use our calculator to figure out what that is. So the ln, natural log of 13/9. So approximately 0.368. Okay, and there we go. And that's how natural log is going to be used. All right, let's start. I need to get this exponential statement alone. There's my two sides. So let's begin by minusing the 4.9. We then have 3 times 15 to the power of 2x should be equal to 61 minus 4.9. So 56.2. Now let's divide by 3. So we have 15 to the power of 2x is equal to 56.2 divided by 3. Let's see if that quickly divides evenly. No, so we'll just leave it as a fraction. Would have been nice, could have saved me some writing. So now we are going to do the log of both sides of this. I need to just remember to write those further back so I have space for my log when I get to that step. All right, so now we're going to do log of base 15 to match that base of 15. And we're doing it to both sides. So when we do that, on the left-hand side, we're just left with 2x. And on the right-hand side, we've got our log of base 15 of 56.2 thirds. Our final step, we need to divide both sides by a 2. So we're going to get x is equal to, so notice how I kind of did two solving processes. In this beginning one, I was just trying to get the exponential statement alone, and once I got it alone, I could use log. But after I did that, x was still not alone, and I once again needed to then begin the process of getting x alone, rather than just the exponential statement alone. And that can happen with more complex equations. So log base 15 Log base 15 of 56.2 divided by 2 should equal a 0.541. And once again, let's make sure we're stating this is approximate 0.541. All right, so over here on the next side, we need to get that exponential statement alone. Let's begin by adding the 4 to both sides, and we get negative 2 times 15 to the power of a negative 3.7n, which should be equal to a negative 38. Divide both sides by a negative 2. We will have 15 to the power of negative 3.7n is equal to a positive 19. Now we're ready to do our log on both sides. So log base 15, log base 15. So then we're going to be left with negative 3.7n. The log base 15 of 19. So final step, we just need to divide both sides by that negative 3.7. And we will get n is equal to, so log base 15 of 19 all over a negative 3.7. And that is going to give us negative 0.294. All right, you'll notice our statement inside that exponent is getting more complex, but hopefully that doesn't actually make anything all that more difficult. Once again, I just see that minus 6, so I'm going to do the opposite and add a 6 to both sides. So now I've got my negative 7, 8.3 minus 4x should be equal to a negative 65.7. Okay, and now let's go ahead and make sure. Come on. Now we'll do our log of both sides. So we're going to do the log of, now right here, we've got something actually interesting, and I should have noticed it before. So let me point this out first. Notice this negative 7. Also, notice that it is not negative 7 inside a parentheses. That negative is not part of that 7. So it only becomes negative after you evaluate the exponent. Now, the reason why I point that out is we are going to run into troubles if we try to take the logarithm of a negative number. It can't be done. So what we're going to do right now is we'll just divide both sides by a negative 1. Negative divided by negative should give us a positive 8.3 minus 4x, and over here a positive 65.7. All right, and now we are ready to do that log of both sides. Once we do that, we then have our 8.3 minus 4x is equal to the log base 7 of 65.7 minus 8.3 from both sides. We now have a negative 4x is equal to a log of base 7 of 65.7 minus an 8.3. Final step, let's divide both sides by a negative 4. And we're going to have x is approximately equal to, now we just got to type that into our calculators. So the log base 7 of 65.7 let's see, minus 8.3 all over negative 4. And as we type that in, we should get a 1.537. Okay, next one, let's just minus our 7 from both sides. Negative 3 times 9 to the power of negative 8r minus 8 is equal to a negative 83. Divide both sides by the negative 3. And now we properly have our exponential statement. All alone, a negative divided by a negative will be positive, which is good because, like I said, we cannot take the log of a negative number. So now we've got log base 9, log base 9, which will then lead us to a negative 8r minus 8 is equal to the log base 9 of 83 thirds. Let's go ahead and add the 8 to both sides. Negative 8r is equal to a log base 9 of 83 thirds plus an 8. Final step, divide by that negative 8. Notice how we're dividing everything when we do division. So r is going to be approximately equal to that huge mess of a problem. Now, what's written above here, I want to make a special note of this right now. This is what you call the exact answer. It is not rounded. We are still using equals. We are not using the approximate yet. I have not done any rounding. That is the exact answer. Exact answers should be used when you're continuing to do your math. However, once you're done with your math, it usually doesn't make sense to communicate to someone else in terms of an exact answer. If I was an engineer and this was part of some equation I was doing, I would not want to be telling my workers to cut the metal to the log of base 9 of 83 thirds plus 8 over a negative 8. That wouldn't make any sense whatsoever. Instead, I would give them the exact, well, the rounded value, rounded to enough decimals to be useful to them. In this case, my example of cutting something doesn't make sense because we got a negative answer. But that's the basic idea. If you're still going to continue to do math, you want to keep the exact answer. Okay, that's why I didn't just start rounding up here in this step. The moment you round, every answer, every operation you do after that is a little bit further away, a little bit further away. Okay, so you only want to do your rounding right at the very end. In these next ones, we are going to be using the bases of exponents to eliminate these logs, and not only that, we need to pay attention to our log properties. So I've got two log base 8s that are being added together. So using the product property, I can rewrite this as a single log of base 8, where on the inside we've got a negative 5x that is being multiplied by a 7, which also then simplifies into negative 35x. So now let's go ahead and let's work on that logarithm statement. So in order to eliminate a log, what I'm going to do is make it into my exponent. I am now writing this as 8 to the power of log base 8 of negative 35x. And the right-hand side becomes 8 to the power of 2. The entire side of both expressions is going to become the exponent of my base 8. Now my base 8 and the log base 8 eliminate, leaving me with my negative 35x, which is going to be equal to a 64. So now let's divide by a negative 35. And that is going to equal, looks like it doesn't like how far down I was. So x is equal to a negative 64/35. All right, so once again, we've got several different log statements here. I need to combine them. I just need one log statement on one side and one log statement on the other. I can't be mixing them, otherwise this inverse isn't going to work properly. So let's go ahead and combine these two. We notice that it's plus again, so we'll use the product property. So I'll have log base 7 of, now this is going to be multiplying, so a 10 times the x minus 6, so 10x minus 60, and that'll equal the log base 7 of 17. So now 7 to the power of log base 7, 7 to the power of log base 7, and we'll be left with 10x minus 60 is equal to 17. We'll add the 60 to both sides. And we got 10x is equal to 77. Divide by the 10, and x is equal to a 7.7. All right, now this time we see that minus here, so we're going to be using the quotient property. So we're going to combine these into a log base 8 of x minus 3 over x minus 6, which will equal 1. Okay, now we've got that. So now I can do my 8 to the power of log 8, 8 to the power of 1, which will leave us with this fraction. I'm going to quickly eliminate this fraction. Having my x in a denominator is going to make it tricky to solve for. So because we're dividing by x minus 6, I am now going to multiply both sides by an x minus 6, leaving us with x minus 3 is equal to an 8x minus 48. Let's get our variable on only one side of the equation, leaving us with negative 3 is equal to 7x minus 48. Now we want to eliminate that 48, so let's add 48 to both sides. We will get 7x is equal to 45. Divide by 7. X is equal to 45 sevenths, I should say, sorry. All right, we see the plus again with these logs, so we know we're going to be using the product property, so multiplying them again. So I'm going to have this 8 being multiplied by the negative 3x minus 6, so a log base 9 of 8 times negative 3x minus 6 is equal to 2. Before we get rid of the log, let's just go ahead and simplify that. So negative 24x minus 48 is equal to 2. Now 9 to the power of log 9, 9 to the power of 2. So negative 24x minus 48 is equal to 81. Let's add that 48. Then we'll have negative 24x is equal to 129. Divide by negative 24. X is equal to a negative 129/24. Okay, so I hope those were enough examples to help you get this figured out. Good luck.